Hello and welcome to our 19th Virtual Research Cafe 10.0. I'm Frank Gomez, Executive Director of STEMnet, and behind the scenes we have Monica Lacon, Operation Analyst for STEMnet. Much thanks goes to her for the logistics and publicizing today's event. The goal of the cafe is to help foster research collaborations across the CSU system and to possibly lead to proposals in the future. The cafe brings together CSU assistant professors to share their works in a relaxed setting, each for 10 minutes long, reason for why it's called 10.0. We hope you'll find opportunities for collaboration and or learn about a new area of research that may impact your own program. Feel free to contact any presenter in the chat box, of course, when they're not presenting. At the end of the 3 presentations, we will all come together to answer questions. We'll also be monitoring the chat box to call questions from the audience. So let's begin. Once again, we have 3 great speakers. This is our last STEMnet virtual cafe. We're going to take August off, but we'll come back in September. Our first speaker is Dr. Sampson Akwafuo from the Department of Computer Science at Cal State Fullerton. Sampson, the floor is yours.
Thank you, Frank. Let me share the screen. Sorry about that. Let me get this. Great, here we go. All right, welcome to today's presentation. My presentation will be on efficient models for disease outbreak prediction and real-time algorithms for disaster response optimization. So in today's presentation, we'll look at the global status of disasters and public health emergencies and the motivation for the research. We'll look at 3 research areas: prediction of disease outbreaks at community levels, and the optimization algorithm for solving the emergency facility location allocation problem. And then we'll look at algorithms for routing of relief, distribution, and improvement. And the global status, a recent publication by the UNDRR, the United Nations Office of Disaster Risk Reduction, highlights the increasing impacts of disasters globally. Within the 20 years under study, most of the statistics, including the total number of persons affected, resulted in a double-digit increase. In this increase, it was found out that many of them happen in low-resource countries. And this is according to a recent publication by the CRED as well. If you see this, you find out that Africa and Asia experience the highest percentage increase between the previous 20 years and the previous 10 years and 2019. So there is need for interventions on public health emergencies and disasters in these regions. Recently, the UN Secretary General Antonio Guterres, that was in April, said that progress on disaster risk reduction must be urgently prioritized as a precondition for sustainable development globally all over the world for environment, disease prevention, and disaster risk reduction. So this intro and a few points I'm going to mention now motivated us to embark on this research. The first one is that there is a need for a coordinated, specific, location-specific disaster response plans in many of the low and medium-income countries. They experience, they are disproportionately affected by disasters, as shown in this table. Most of these countries experience the highest, and there's need for pre-disaster in planning for disaster outbreak or disaster or public health disease outbreak. There's need to locate emergency operation centers, depots, or we can call it points of dispensing, PODs, and minimizing the cost of delivering interventions to affected locations. This can be done by developing computational models that will optimize using the little resources available in this regions to ensure adequate delivery. So evaluating impacts of different interventions and then reducing casualty figures. These are some of the motivating factors. So there, for the research component, the first part is on development of machine learning models for outbreak prediction, disease outbreak prediction. So it uses data from disparate sources, data like environmental data, geospatial data, and historical public health surveillance data to develop models that can predict an outbreak of a particular disease in a particular location. So for this study, we are starting with Lassa fever. Lassa fever is a disease that's endemic in most regions of West Africa, and there have been some incidences in the US as well. And so we are concentrating on North Central Nigeria and IDPs, internally displaced persons camps. There are so many camps in these regions, and in the last 1 year, there has been so many outbreaks of this Lassa fever in these regions, in these camps. So we are trying to predict and then prepare. So the second part of the research is on depot points of dispersing location allocation problem. So what appropriate machine learning algorithms can we use to optimize displacement? And part 3 of the research is on algorithms, developing algorithms for dynamic route construction improvements. Whenever there is an outbreak of disease or disaster, sudden disaster occur, if there is a sudden disaster, how do we provide relief materials to the affected regions using whatever is available? If it's motorcycle, if it's a low capacity vehicle, and resources, optimizes that so that instead of waiting for donors from foreign countries who reach them and deliver. So this is what the third part is all about. We involve the integration of new nodes in real time, places affected, and then using emergency ranking with priority on most vulnerable population. So we have not done much on part 1 of the research, but on part 2, of the research, which is an emergency facility location problem. We can define the problem using these equations. We'll go to the preliminary output from the second part. So here we are developing a modified K-means plus algorithm. This takes in initial center EOD from the location, put it into the system, and develop an improved algorithm that will tell you where to site these centers and the number of medications needed or vaccinations, the number of vaccines, other interventions needed in order to effectively serve the local community. So we apply this in the study area, and we're able to divide the country into 38 regions here. And the output also gave us the longitude and latitude of these new centers, it's called cluster centroids, using the algorithms. And again, these algorithms will produce and improve time complexity compared with existing the K-means plus. And this algorithm can be evaluated using silhouette analysis. Here is explanation of a silhouette analysis. So we applied it, and we were able to get between 36, 35, and 36, 38, and 40. And here we have that the base is 38. Right, so that's the third one is about initial route construction and how it can be improved using data, using fitness calculation from AI-based algorithms, and the rest of them. So seems my time is up. And we use the emergency severity ranking to know where to visit because the resources are limited. Thank you.
Great, thank you, Sampson, for your talk. There'll be questions probably during the question and answer section. Our next speaker is Charli Sakari from San Francisco State University, the Department of Physics. Charli.
All right, thank you, Frank, and thank you, Monica, as well. So yes, I am Charli Sakari from San Francisco State, and I'm excited to talk to you today about my work in Galactic archaeology. Before I dive into that, though, I'd like to introduce my research group. Here I am with all of the students who have worked with me, current and former students at SF State. And I'm not gonna, one of them I think is actually here today, Pedro Silva. And I'm not gonna have time to dive into the interesting research projects that all of them are working on. But if you're interested, you can ask more later. Instead, I'm going to give a general overview of what we all do. And so often our field is referred to as galactic archaeology. And so to understand this, we can think about terrestrial archaeology, where scientists dig up old artifacts and use those old artifacts in their current state to understand the behaviors of civilizations past. And so we do a very similar thing, but instead of artifacts, we're looking at old stars. And instead of understanding the behavior of civilizations, we're understanding how galaxies assemble over time. And so we can look at a galaxy like this. This is the Andromeda Galaxy. And we can look at the stars there, and we can ask questions like, where and when did these stars form? How did they get to where they are now? How is this galaxy like others? And then ultimately, are the properties of this galaxy consistent with the physics that we believe underlies the universe? And so we know quite a bit about galaxy formation from observations and from simulations. And so we know that one way that galaxies assemble over time is through the accretion of dwarf satellites. And so this artist's conception demonstrates what this is. So here we have a spiral galaxy, and orbiting around that spiral galaxy, we have a dwarf galaxy. And as the dwarf galaxy orbits, it's broken up and disturbed by the larger galaxy, which forms these streams that then wrap around the larger galaxy. Over time, those streams are going to dissipate, and those stars are going to become just part of the larger galaxy. And billions of years later, you might not even know that they originated in a dwarf galaxy. And so we actually see this process happening right now in the Milky Way with the Sagittarius dwarf spheroidal galaxy. And we infer that it's happened many times in the past. And so there are questions that we'd like to know the answers to. In the Milky Way, we'd like to know what types of galaxies are accreted. Where did the current stars that live in the Milky Way originate? How do the star clusters in the Milky Way fit into this picture? And then ultimately, how is this process of ongoing accretion different in other galaxies beyond the Milky Way? And so I focus on studying these questions through the chemical compositions of stars. And to understand why this is useful, we can think about how stars form and evolve. And so this is a schematic of star formation and evolution from NASA. And so we can start here in the center in a star forming region or nebula that is made of gas and dust. And so stars form out of that gas and dust. Their evolutionary paths differ depending on whether they're a low mass star like the sun or a more massive star. But in both kinds of stars, these stars produce new elements during their lifetimes, whether that's through fusion or other processes. And then at the end stages of their lives, low mass stars would go through a planetary nebula phase, higher mass stars would have a supernova. But in both of those types of stars, they blow off their outer layers and deposit that material into a new star-forming region. And that star-forming region is now enriched with the products that were created by those stars. So what we see is that over time, we have this cycle where stars form out of increasingly enriched material. And that means that their compositions change over time. And this is a process that we refer to as the chemical evolution of a galaxy. And this is also particularly interesting because here is a periodic table of the elements, and it is color coded by the astrophysical site, so where the different elements form. And each element forms in a slightly different place, in a slightly different way, and at a slightly different time. And so, for instance, the supernovae that I spoke about are in green. The typical pathways for low mass stars are light blue and yellow. One of the types that I'm interested in is the merging neutron stars, which are in orange. And we're particularly interested in how, where, and when those elements formed, which is the subject of a collaboration I'm part of called the R-Process Alliance. But what we can see from this is that each of these elements gives us a different insight into the types of stars that lived and died before the current star we're looking at was born. So how do I get this information? Well, I take a star that I'm observing and I take the light and spread it out into a spectrum. Typically not using a prism like this, but the process is very similar. And so you might expect that we'd have this nice rainbow spectrum like we would see with, for instance, sunlight going through a prism. But with our high quality spectrographs, we can actually see that there are these dark bands or absorption lines on top of the rainbow spectrum. And these absorption lines are caused by the presence of atoms in the atmospheres of the stars that are absorbing the light that is coming from the interior. And so here is another way of looking at a spectrum. Here we have set the continuum, the rainbow level at 1, and each of these dips here is a different absorption line. And I've labeled them in this very small region of the solar spectrum by the element that creates that spectral line. And remember that each of these elements forms in a different place at different times. And so we can use this information to understand how much of an element is present in the stellar atmosphere, but also we can get an idea of the different types of stars that existed before the star was born. So just to remind you, I talked about this cycle of chemical evolution. And one of the key points here is that the chemical evolution with time, or the relationship with time, actually changes depending on the environment. So chemical evolution looks different in a low mass galaxy than it does from a high mass galaxy, simply because low mass galaxies have fewer stars. So they don't have as many stars enriching those nebulae in making new stars. And this is a really key result because this means that we can actually answer these questions through observations of the chemical abundances of stars. We can figure out, what types of galaxies, what mass they are, where current stars originated, how globular star clusters fit into the picture. And then as well, I'm not going to have time to talk about this, but this is another field of research that I'm involved in, is thinking about taking these observations and moving them beyond the Milky Way to even more distant galaxies like the Andromeda Galaxy. So that's something that we can also do. So this is a really, really brief overview of the type of work that we do in our research group, but there's a lot of room for collaboration here. So in particular, those of you who may work on the physics or chemistry of the R process, that's the process that creates the orange elements here. My research group is very interested in understanding that, or really any process in the, we're interested in those too. As well, astronomy nowadays uses a lot of computer science, mathematics, and statistics. And so if you're interested in, collaborations to improve our analysis techniques, particularly our automated analysis techniques, or working with large data sets, we certainly could use that collaboration as well. And of course, any other ideas you have, I would be welcome to. But in the last few minutes here, I really want to focus on an interest that I've developed as a faculty member in my last 3 years at SF State, which is more working on the education about climate change, in particular, bringing the astrophysical perspective on climate change. And so in 2019, when I joined SF State, I was part of a group that we started called Astronomers for Planet Earth. And this is a group of astronomy researchers, students, public educators at museums and planetariums, amateur astronomers, basically anyone who works in astronomy. And we are interested in bringing the astrophysical perspective on climate change to the public and to ourselves, to each other, to our students. And one of the things that I have done is I was part of the group that founded an educational working group. And we're interested in really collecting and curating and developing resources for our members to use in the classroom, both in K through 12 and higher education, but also in the educational and public outreach domain. And so if you're interested in learning more about A4E, here is our website. We're also on social media. We also have fabulous videos that I really want to plug because one of my research students, Jessica Agnos, has made several fantastic videos for public outreach, including one set to a poem by Maya Angelou called A Brave and Startling Truth. And so I highly recommend that you check those out. But amongst other things, what we're really focused on in this group is the astrophysical perspective, and astronomers have a lot to say here about Earth's connection with the sun, Earth in an astronomical context, exoplanets beyond our solar system, the impossibility of traveling to them, the physics of climate change and solutions, and many, many more things. So if you're interested in collaboration on that, I would welcome that as well. All right, with that, I will go ahead and stop. So thank you all very much.
Thank you, Charli. Very, very interesting talk. Space is always very spacey. Okay. Our next speaker is Petr Vozka from Cal State LA, the Department of Chemistry. Peter.
Hello, everyone. I hope you can hear me well. I hope you can see my screen right now. First of all, I would like to thank the STEMnet for giving me the opportunity to present my research today, and also thank you all for attending this talk. My name is Petr Vozka. I'm from the Department of Chemistry and Biochemistry here at Cal State LA. Here is my brief overview. I'll talk a little bit about my research background so you can understand why I'm doing what I'm doing. Then I will introduce the complex chemical mixtures, the terminology we're using, comprehensive two-dimensional gas chromatography. And I'll talk about 2 projects focusing on plastic waste and possible collaborations. So I got my BS and MS in Prague, in University of Chemistry and Technology. If you ever travel to Europe, please visit Prague. It has been built in 14th century. It's a beautiful city. And as you can see, our titles have a little bit like longer names than here in US. So my bachelor was in chemistry and chemical technologies, and then master in chemistry and technology of fuels and environment. And that's where my focus starts shifting toward fluid fuels and environment. I got my PhD and postdoctoral research experience at Purdue University when I already focused on alternative aviation fuels. And most of my research was funded by the US Navy. I work with a lot of the Department of Defense organizations. And I really love the idea to see that how the fundamental research can really become applied. And I joined CalState 2 years ago. This is my second year. I'll be starting my third. And I set up a complex chemical composition analysis lab. And so what we do in this lab, we analyze complex chemical mixtures. And how we do it by using comprehensive two-dimensional gas chromatography. Now in the few next slides, I'll introduce the term complex chemical mixtures and then the GC by GC. So what are complex chemical mixtures? In general, anything you can think of. A complex chemical mixture is defined as a mixture that consists of tens, hundreds, or thousands of chemicals, and of which the composition is quantitatively or qualitatively not fully known. So mostly we're focusing on fuels, petroleum products, plastic fuels made of plastic waste, and microplastics. But I'll get to that in a little bit. Two-dimensional gas chromatography. This is the instrument we're using on a daily basis. If you're familiar with gas chromatography, let me see if I can turn on the pointer here. So in one-dimensional gas chromatography, on conventional gas chromatography, you only have one column. So the separation mechanism is limited. Imagine the column is separating based on the boiling point or polarity. So all the compounds in very complex chemical mixtures that have similar properties, either boiling point or polarity, you can separate on one column. But in two-dimensional gas chromatography, we have two columns with two different separation mechanisms. So those that are not separated on the primary column, they can be further separated on the secondary column. The great thing is we only need 1/5 of a drop, and we can give you very detailed chemical composition. What do I mean by that is this, for example. So this is the meme. You may remember how it started, how it's going. So this is conventional gas chromatograph of jet fuel, where you can see probably 100, 150 peaks. So one would think maybe, there is 150 compounds in jet fuel. This is how does it look now with two-dimensional gas chromatography. This is a beautiful 3D model that we never use. We're actually using this chromatogram, which is 2D model, and it's basically the view from the top. And then basically each of these blobs is one compound. So right now we know that in jet fuel, there is more even than 2,000 compounds. And if you can figure out what is each compound, you can also figure out how much. So the difference between this 2D chromatogram, so all these compounds, this is the first dimension, the first separation mechanism. So all these compounds with same retention time, they would elute here as one peak. So you wouldn't be able to further figure out what are these compounds. You would just have like a coelution of these compounds. Now, if we can do this now, how are we using it? So you have probably seen these terrible pictures of the polluted ocean. And so at least 8 million tons of plastic end up in our oceans every year. The more disturbing fact is that this only accounts for 3%. Okay, so you may ask, where is the leftover? Well, 76% is actually landfilled. Okay, so what it means that you probably know the plastic waste doesn't biodegrade, so it's with us almost forever, and it's accumulating with a dramatic speed. So and together with the plastic waste, we are actually getting the microplastics. Okay, only a small percent of plastic waste is recycled or reused in US. I think it's approximately 9%. So I would like to talk about two problems.
It appears we lost Peter. Hopefully he could come back on soon. Oh, he may be coming back on. You there, Peter? Okay, Peter?
I think I lost the connection. What did you hear for the last time? Have you seen this slide? Yeah. Okay. So 2 projects. I apologize. Let me maybe turn off my video. 2 projects. So we don't have a reactor, so we don't convert the plastic waste to fuel, but we collaborate with my previous 2 universities, and they sending us the fuel samples. And what we can do with these very complex fuel samples made of plastic waste is we can analyze them via GC by GC. And we can, for example, compare these fuel samples. So what Purdue is using is called hydrothermal processing technology. So we can then compare the chemical composition of the commercial diesel versus the plastic waste diesel. This is visual comparison only. So we, of course, don't use this to claim any results. But because we know in the chromatogram which compounds elute where. Meaning we can distinguish between carbon numbers, we can distinguish between any hydrocarbon classes, we can get quantitative results, okay? So what we can, for example, do for you is to send us a sample, we can tell you for every hydrocarbon class, and these are just some examples, and for every carbon number, we can give you the weight percent composition of your sample. Okay, now why is this important? Because then, for example, we could develop the reaction pathways. So for their process, we were able to develop the reaction pathways, which can then serve to modify and fine-tune their process. With Prague University, we work on the pyrolysis. So it's similar process, a little bit different. And so anytime you have a fuel sample, you need to measure the chemical composition, the fuel properties in order for these fuels to be approved to use in either gasoline or diesel engines. So that's one thing we can do. Another thing, what are we doing is we focusing on the microplastics, but not on the microplastic itself, but on the compounds that are absorbed on the surface. So for example, you know Dr. Holland, she's from Coal State Long Beach. So in 2019, she published a paper where they found over more than 500,000 microplastic species in a cubic meter of Los Angeles River. What is microplastics? Well, microplastic species have been discovered basically in every location you can think of. It was in the Mariana Trench, in the Arctic ice. But the more disturbing fact is that we are breathing the microplastics, we're eating it, and we drinking the plastic infused water every day. Microplastics is defined as any particle below 5 millimeters. And this, you have may seen these graphics from Reuters. I think if you have not and you ever talk about this in your class, use these. So this is how much you eat every or digest every week. This is how much every year, and this is how much in the lifetime. Now, microplastics have different shapes and sizes. As you probably know, it's not coming only from the plastic waste, but from the clothing. We intentionally put the microbeads in our personal hygiene products. And as I said, we're eating it, breathing and drinking it. But the question is, since microplastics is an amazing absorbent, and it can absorb a lot of compounds. Many compounds have been found absorbed on the surface. You know, feminine hygiene products, drugs, polyaromatics, a lot of compounds. So the question for us is, first of all, can we detect these compounds in micro? And are these actually dissolving in our body? Okay. So the potential collaborations, we're looking to explore the desorption mechanism of these organic compounds absorbed on microplastics in human body or human body liquids. So we would be looking for some biologists, biochemists, or anyone who works or is interested in working and helping us to see if these compounds would actually dissolve in the human body or if they would just go through the human body. And then we also are always happy to collaborate with anyone that or whose research is related to analysis of complex chemical mixtures and doesn't have instrument or doesn't know how to do it. And of course, with samples that are suitable for the GC by GC, which are usually volatile and semi-volatile compounds. And any other potential ideas you may have, we would be very happy to discuss with you. Thank you.
Great, thank you, Peter, and certainly thank you to everyone for your presentations. We now will open up the floor to those who would like to ask questions. And if you can, you'd either raise your hand or turn your screen on. So we'll open it up.
I think there is a question there for me.
Yes, why don't you answer, Sampson?
Okay. Let me share this again.
So the question was from Peter Behel. When you're accounting for vulnerable populations, doesn't this take the chat one? Doesn't this take place along a spectrum, i.e. vulnerable, very vulnerable? How is this absolute threshold of vulnerable populations determined?
Thank you. I was gonna show the slide to better answer that. Anyway, yeah.
You
So
want to show it?
yeah, can I share? Yeah. This. Again. So as a no worry, I'm gonna share it. Right, Peter, thanks for the question. So yeah, the yes, yeah, we have like a relative, there is a relationship between the most vulnerable population, the, let's say, very vulnerable population and the least vulnerable. I wish I can share the presentation so that you can understand it, that here, the number of persons in that location determines the classification, whether it's most vulnerable or least vulnerable. Remember that these locations will come up when the vehicle is already in motion. So the control center will try to contact the driver of the vehicle that after location D, for example, do not proceed to location E. There is a new location, location Y, and it has higher vulnerability. What makes it higher vulnerability? Because of the number of children or number of age population. So the population in that location, if we have higher number of age persons or higher number of children and women, then compared to the location E, which initially the driver was supposed to go. If we have the higher number in this new location, then the driver will be diverted to serve the new location. Let me try to show this. Yeah. It should show now. Oh, so it didn't show. Okay. So I don't know why it didn't show. That's how we group it. Yes, it's not absolute number, there's relativity between that. I don't know if I've answered that.
Great, thanks. Thanks,
Okay.
Sampson. Curtis?
Peter, I think you had your hand up first. You want to go
You have
ahead?
another question? You have another question, Peter?
I do, but I'm going to yield the floor for the moment and go ahead, Curtis.
Okay. Okay, sounds good. Well, just wanted to thank everyone for the presentations. Really found it interesting, all of them very interesting. I'm Curtis Asplund. I'm at San Jose State in the Physics and Astronomy department. And mainly I just wanted to connect with you, Charlie. It's good to, virtually meet you, and thank you for the talk. And I'll reach out to you separately about the climate change stuff, because I think it's something I've tried to do in my astronomy classes. I've taught Astro 101 for a couple of years now, and like last year, we definitely did a big chunk on climate change because it's important. And maybe as a question, I was just curious if you wanted to say something about like the reaction you've gotten from your Cal State students, like when your Astro students, because sometimes they're a little surprised. They're like, wait, I took an astronomy class. Why are we talking about, Earth? Yeah, so anyway, I was just curious if you wanted to share something about the reactions you've got.
Yeah, so I have mainly been teaching physics, actually, physics with calculus, one of the three. And so I've been including it sort of in the thermodynamics part mainly, but also we have a little section about black body radiation and, the greenhouse effect in general. And I think I think some students are very surprised at how significant the connection is, but I think they also appreciate it too, because when I first started teaching this class in particular, there's a lot of engineers in there, and they have specific interests that, I've, like for instance, cars that don't overlap with my interests, but I've kind of learned like, I can teach them about biofuels, right? And we can talk about that and engines and all those things in this class. And so their interests have also kind of led me to broaden my own interests as well, I think. But the feedback we've gotten in astronomy is that they often, I don't think at SF State there's been much resistance or surprise. Generally, students are very eager to talk about these things and to find ways that they can do something about it. Yeah.
Great. Yeah, thank you. Yeah, I'll be looking forward to talking to you more.
Great, thanks. We're going to go to Yazdan, then Peter after.
Okay, thank you very much. My question is about thermodynamics, given the fact that Charlie was talking about that. Would you please a little bit more talk about that, what you are doing on thermodynamic aspect of galaxies? A little bit more. Thank you.
Yeah, so galaxies, some types of galaxies have gas in them, others don't. And so I, for the most part, don't care about the gas in the galaxies. So that's sort of where the thermodynamics part would come in. So mainly when we're talking about galaxies merging, we're talking about stars. And so it's just pure gravity interactions. Where the thermodynamics comes into my research more is with the actual modeling of the stellar atmospheres and using the spectral line strengths to infer the abundance, because then we go through a full, analysis of the, taking the temperature and the, properties of the atmosphere into account when we do those, solve those equations. Yeah, so that's a really kind of vague description, but yeah, did you have a specific question?
Charlie, yeah, the specific question is about entropy production, because, one of the way that we can measure what happens in thermodynamics is entropy generation. So did you do something about the entropy generation of the galaxy forming or galaxy formation?
So I have not, no, but I think there are people who do that, as well as in stars. There's a lot of people who look at entropy generation in stars. Those are people who are more on the theoretical and simulation side of things.
Yes.
Yeah.
Well, okay, very good, because I'm very interested in that. After that, I think I will connect to Mr. Splon too, because I think because we are at the same university, and I hope I can connect with you. Thank you.
And I see Ron Marsky is here as well. I don't know, Ron, if you have anything to add to that.
No, not at all. It's a really interesting area, though.
Thank you.
Peter.
Thank you. My question is for Dr. Vozka, my second question, and has to do with the presentation of the gas chromatography measuring. And I'm involved in the area of stress-related effects, and know that one of which is, exhaled PCO2 or carbon dioxide. And so my question is, how fast does this display analyze? Does it take, large blocks of time, or can it be abbreviated into shorter blocks of time?
So it's a great question. Depends how much you need to separate your mixture. But if you have very simple mixture, many of these gas chromatographies have been used online. You can connect them to the system or a reactor, for example, and it would sample anytime you want to, and then you can get very quick results. We're talking about minutes, even seconds, if you set up your method well. But if you have a very complex chemical mixture and you need to separate these compounds, that may take 10, 20, 30 minutes, hours, but could be connected online, has been done, many times, and then you can get very quickly your results.
Excellent. Thank you very much.
Any questions from our audience? I do have a quick question for you, Peter. On you mentioned the U.S. recycles 9%. How do we compare to other nations?
Europe recycles a little bit better. China, for example, worse. India worse. It's not that bad. Usually these percentage people are shocked, because whenever you say microplastics, people imagine polluted ocean or waters, but we're forgetting that we're breathing these microplastics on a daily basis as well, because it's sitting in landfill, it's degrading and then becoming microplastics. So 9% recycling is also a little bit if you think, most of you see all these colorful garbage cans where we, separate each and everything. But yeah, it's not very easy, and it's a hot topic, the plastic waste and microplastics. So
Great, thank you. Questions? Okay, if not, we're going to give you back some time in your day. We certainly appreciate you attending, and thank you to all of our speakers for very, very interesting presentations. Just very briefly, we do have a couple of events coming up. Next Wednesday, we have our webcast on innovations in STEM teaching and teacher training and development. It'll be a last one. We take August off for our webcasts and virtual cafes. Our next cafe will be September 21 at 11 o'clock on Wednesday. So we will be sending out information on that. So hopefully you can attend. It's always good to get 3 little mini seminars together, and certainly from different disciplines and different campuses. You probably won't see that anywhere else in the CSU. So it's great that we have people attending, and I know it's through summertime, but if you're not traveling, then why not step in for an hour once a month, huh? So thank you to all of you for attending the cafe. Enjoy the day and have a good rest of your week. Take care. Goodbye.